Greetings, AP Physics students. It's Monday afternoon in your reality. In my reality, it is Saturday afternoon, about 20 till 2. So today we're going to start chapter 23, which is on circuits. And so the goal today is I'm going to use this FET simulation. And this is the lab that you're going to use tomorrow on a lab on circuits, and then another lab that you do on Wednesday with light bulbs. So it's a cool program. You can change any number of parameters, like you can change the voltage of the batteries, you can change the values of the resistors, you can change the light bulbs. And the cool thing about this is that it kind of matches all the calculations in terms of it's built up with the idea that all the wires have no resistance, and so the only resistance will come from either resistors or light bulbs or something like that. So as we go through this, I'm going to show you some different setups, and then we'll see how that relates back to your VER calculations and your power calculations, and how you deal with series and how you do with parallel. So we're going to start off with a fairly simple one. Actually, let me go turn out these lights. Hold on, I'll be right back. Maybe cut down on that glare a little bit. Okay, so this is as simple as the circuit can get. So I've got a battery right here that's set at 10 volts. Now, the default program when you set a battery in here is the default program is to set it to 9 volts. So if you want to change something, if you just highlight that, then you can drag and change the voltage across here, okay? Now, the other thing that you will notice is that when you look at this in terms of the current, so right now I have it showing up here, I've got it clicked on showing the electrons. So this is the actual path and reality of what's happening. So you have electrons here in the negative terminal of the battery coming out. So this is fish, okay, fish. You're leaving the battery, you've got skittles. You're going around, you're hitting this branch, boom, here's this resistor. So this is what you have to fight through. This is where you're going to offload the skittles. You're coming through here, you've got no skittles, you hit the positive terminal, you go through the battery then recharges those electrons, gives them skittles, they leave, boom, there you go. So this is the actual path. So if you're more old school, if you're the OG, okay, then this shows the conventional idea of a current. So that's going from the positive out around like this. It really doesn't make any difference. It doesn't change the calculations. It's just a personal preference thing. So you can go old school. Hey, Ben Franklin, he said the positives are flowing. Or you can go conventional and go, in reality, it's the electrons and it doesn't change any of the calculations. It's a personal preference thing. Okay, so we've got a 10 volt battery and we have a 10 ohm resistor. So if you hit the show values, okay, if you check that little button right there, then it shows, oh, this is a 10 ohm resistor. Now, and I'll show you this a little bit later, but resistors are color coded. So let me get that, let me change that so you can see this. So this has like a gold band, and it's tough to see, but that's like a green, a black, and a red band. So if you really get into, like you're going to be an electrical engineer, if you're really into circuits, there is a code that exists that in the colors, these colors on these resistors tell you the value of the resistance. At one point in my life, I knew some of them, that ship has sailed. But the only thing I want you to realize that as you change the resistance, you change the color codes on this. And I'll show you this. And this program actually changes those codes when you change the resistance. So here's what I want you to see right now. I've got a 10 ohm or 10 volt battery. I've got a 10 ohm resistor. This is as simple as it gets. It's one circuit, one battery, one resistor. Now, this current, now in reality, if you're using like the old school amp meters like I showed you, that would have to be hooked up in series. This is cool, and we actually have these. These are called contactless amp meters. So all you do to use this is if you hover that over the wire, basically what it does is it senses the magnetic field associated with it, and then it converts it into a current. So this is a 1 amp current. The voltage, you actually have to hook that up across a point that you want to measure. So this amp meter, it's cool. All you have to do is slide it over the wire. It's going to show you the amperage. The voltage, you actually have to touch the leads to the point that you want to measure across. Okay, so 10 volt battery, 10 ohm resistor. So now, when you do the math on this, come on. I want to do it. So we'll get fancy and oh, they changed my program. There we go. Let's go with that. Okay. So if you look at this in terms of varying it up, hopefully y'all can see that, because my view is completely different than what you see up there. So what we had is that we had a 10 volt battery, we had a 10 ohm resistor, and this is like the shortcut way of drawing a battery, long and short. And then the resistor is just a squiggly line. So if you look at this in terms of trying to vert it up, if we take the voltage, which is 10 volts, we divide that by that 10 ohm resistor, oddly enough, we get 1 amp. So if we go back to that page, yep. So that's exactly what that current is showing. Okay, we got current, simple circuit, 10 volts. It's losing all that. Fish, you're losing all your Skittles right there on that resistor. Boom, here we go, easy peasy. Now, next logical question. Well, what happens if we change things up? So what we're going to do next is I'm going to connect this wire right here. Come on. Now, what's happened is that this is 2 resistors that are in parallel. Okay? So there's a couple of things that I want you to notice. When I did that, notice that my voltage stayed at 10 volts. Okay? That voltage still stayed at 10 volts. My current, though, went to 2 amps. So this is a situation where your mom is cooking in parallel. Same voltage drop across both of these, 10 volts, because these are both 10 ohm resistors. So notice that the current went up. It's because what's happening is that your mom, Jackson, okay, your mom is just not feeding Jackson. Now Brooklyn is home, and now she's feeding Brooklyn as well. So what's going to happen is that these resistors are in parallel. Now, how you handle parallel? On yonder purple sheet, down here about 2/3 of the way down, 3/4 of the way down, you have 2 equations for resistors. One in series and one is in parallel. So what's happening here is that we have, these are in parallel. So down here, you have 1 over RP equals the sum of the inverses of the resistors. So here's what I've got. I've got 1 over 10 plus 1 over 10. So if they are in parallel, okay, then you add the inverses. So this is going to be 1 over 10 plus 1 over 10, and then we're going to take the inverse of all that. So a lot of times what you want to do is that you want to talk about what's called an equivalent resistor. So if I take these two resistors that are in parallel and add them together, that gets me 2 over 10. I take the inverse of that, I get 5 ohms. So here's what's happening. When I take that battery and I put a 10 ohm and a 10 ohm, okay? So I have two 10 ohm resistors. So that's the equivalent of having one 5 ohm resistor. So mathematically, when you look at trying to vert it up, a lot of times what you want to do is find the equivalent resistance. Oh, the equivalent resistance, even though I have two resistors that are in parallel, the equivalence is like having one single 5 ohm resistor. Now look what happens. When I take those two resistors and I put them in parallel, notice that it drops the overall resistance in the system. So if you go back to Jackson and Brooklyn, okay, Mom cooks in parallel. So by cooking in parallel, she's going to decrease the resistance because Jackson and Brooklyn are both getting fed. They don't have to argue with each other like, oh, come on, man, I wanted some more lasagna. No, I want, okay? And so instead of both of them fighting for the same lasagna, they're both getting their own pan of lasagna. Hey, life is good. The resistance goes down because Jackson's mom cooks in parallel. Now, the downside of this is that she's going to have more food that's going to flow out of the kitchen. So mathematically, we still have that 10 volt battery, and if we vert it up and we divide that by that equivalent resistor of 5 ohms, so the two 10 ohms in series is like having one single 5 ohm. I divide that out, oddly enough, I get 2 amps. So if I go back to this, oh, not what I wanted, wrong one. So this is why when I put these two resistors in parallel, the current goes up to 2 amps. Now, interesting thing happens. Okay, let's look at what's going to happen when I measure the amperage across this wire. So we have some options. Option number 1, they're both still going to be at 2 amps. So option 1, this is going to be 2 amps, that's going to be 2 amps. Boom, there you go. The other option is that this thing is going to get split. 1 amp, 2 amps. Or excuse me, 1 amp and 1 amp. So let's see what happens. So if I drag this over here, oddly enough, stretch that a little bit too far. When I put that over there, I get 1 amp. Move it over here, I get 1 amp. So this is Kirchhoff's rule. I have 2 amps coming in. That's going to get split into 1 amp and 1 amp. Now in this situation, everything is nice, everything is simple, everything is equivalent, 10 ohm, 10 ohm, there we go. Now, let's change it up a little bit. So I want to take this one, and instead of having 10 ohms, I'm going to move that up to 20 ohms. Okay? Now, let's find the equivalent resistance. So now I've got a 10 ohm and a 20 ohm that's in parallel. So if I do the math, I'm going to take 1 over 10 plus 1 over 20 and then take the inverse of that. So since I've got to do my own calculations, brutal. So I'm going to take the inverse of I hate this calculator, by the way. Negative 1 plus 30 to the negative 1. Get a certain value, and then I'm going to take the inverse of that. I get 12 ohms. So now, if I look at this in terms of Ver, right? So then I've got my 10-volt battery, and that's like saying I have a single 12-ohm resistor. So if I take 10 and divide that by 12, hold on. I get hold on. I've managed to break physics. Back. The old, I punched something wrong into the old school calculator, went with the simple one, and I got the right answer. I don't know what happened. So here's what we've got, because I was afraid I broke physics for a second. It's like, well, this is bad. Okay, so notice that the current here is 1.5, all right? Because mathematically, and this is where this went wrong, okay? So this is when I take the 10 plus the 20, and then the inverse of that, I get that to be not 12, but 6.67. So then if I take the 10 and divide that by 6.67, then I get 1.5 amps, okay? So that's why the momentary flipped out. I was like, whoa, this is bad. Either the program was wrong or the calculator went bad. Thank God the calculator went bad and it didn't break any physics. That'd been awkward. It's like you guys come in on Monday. What happened to physics? I don't know. Berkamp broke it over the weekend. Have no idea what happened, but he did. Okay. So what we've got is that we have a 1.5 amp current right there. Okay, it's cool, right? So now, but an interesting thing happens. When I move that current to here, that becomes 1 amp, so that's the 10 amp. And oddly enough, when I move it over here, then I get a 0.5 amp. So notice that half plus the 10 still add up to 1.5. That's cool. But if you look at this in terms of, you don't want to apply like human emotions to a physical structure like this, but in this situation it kind of makes sense. So here are these electrons, okay? This has the 20 ohm, that's a higher resistance. This is 10 ohm, a little bit easier, less resistance. So basically what happens is that when this field gets to this point, since this has more resistance, more of that current is going to go through the 10 ohm, because that has less resistance. Less of it's going to go through the 20 ohm over here. So it's still going to recombine and end up at, well, I have no idea what just happened. It's still going to end up at 1.5, but it's going to get split, but it's not going to split evenly. So the inverse relationship is that the one that has the higher resistance is going to end up with less current because it's harder to get that to go through there. Okay. We got that one. Now, when you look at the voltage, so notice that even though this is still a 20 ohm resistor, the voltage drop is still 10. If I come over here and measure the voltage drop across there, notice that's still 10 volts. So even though I've shifted it and made the 20 volts and the 10 volts, notice that they still have the same voltage drop as the 10 volt battery. And even if I measured it all the way across between the beginning and end of the circuit, that's still going to be 10 volts. Now, interesting thing happens. If you look at this mathematically, I go, okay, let's just say we don't know what the voltage is. We want to ver this up. So if you look at this going into here, so let's say that I know I've got a 10 amp current, okay, 0.5, and I've got a 20 ohm resistor. So if that's all I know, if I take that 0.5, if I ver it up, if I take that 0.5 amps, multiply that by my 20 ohm resistor, oddly enough, I'm going to get 10 volts. If I move this thing over here, okay, now I'm up to 1 amp. 1 amp times 10 volts, or 10 ohms, gets me 10 volts. So this is another reason why we wire houses in parallel, because they're going to have the same voltage drop across that being hooked up in parallel. Okay, so that's what's going to happen if they're in parallel. Now, let's talk about what's going to happen in series. So let me do some reworking of this. Trash that. Trash that. Cut that. And let me change that back to 10 ohms. Okay. And put the wire in here. And then I'm going to hook that up. Okay. Now I have two 10 ohm resistors that are in series. Okay? So 10 ohms, I still have the voltage of 10 volts. Now, when you add resistors that are in series, okay? So if you come over here, boom, find the sheet, series. If they're in series, you just add them straight up. So the resistors in series are just, that's a horrible sum, are just the sum of the resistors. You don't have to do the inverses of them. So when I had that 10 ohm and that 10 ohm, okay, oddly enough, that adds up to 20 ohms. So having two 10 ohm resistors in series is the equivalent of having one 20 ohm resistor. Now, if you go back to the analogy of Jackson and his sister Brooklyn, okay, now his mom cooks in series, okay? His mom's going to cook in series. So what's going to happen is that now Jackson and Brooklyn are going to have to fight over the same pan of lasagna, okay? Same pan of lasagna. It's like, oh, come on, man, sis, I want some. Brooklyn's going, no, Jackson, you can't have me, okay? So what's going to happen now, because we have the equivalent of 120 ohm resistor, so now we're going to sit there and go, okay, if you ver it up, so I've got a 10 volt battery, and I divide that by the equivalent of 20 ohm resistor, I get a half an amp. So now if I go back to this program, notice that that's what that current is. That's a half an amp. Now, when I measure the voltage across here, okay, now the first time I do this, I'm going to go all the way across from one end of the batteries, or from one end of this resistor, all the way up to the other resistor. Notice that that whole thing is 10 volts, okay? So I'm dropping 10 volts. Fish, you left with your Skittles, you're dropping all the Skittles across those resistors, okay? So that's a 10 volt drop across the whole thing. But if I look at what's going to happen across each individual one. So now if I just measure the voltage drop across this, notice that this is 5 volts. So what's happening here is that Fish is dropping half of his Skittles here, and he's dropping the other half of the Skittles up there in that other resistor. He's not going to drop them all on the first one. He's going to split it. He's going to go in. He's looking down range, and he's going, man, I gotta go through 2 resistors. I don't want to drop all my Skittles on the first one. I need to save some, right? So he's going to have a 5-volt drop here and a 5-volt drop up there. Okay, so in series, look what happens to the current. The current goes down. So if Jackson's mom cooks in series, the resistance is going to go up because Jackson and Brooklyn are fighting for the food, okay? But notice that the current goes down, okay? The current goes down. So basically, Jackson's mom sits there and goes, hey, you two are going to fight over this deal. I don't want to hear it. I'm going to give you guys even less food. And it's like, oh, seriously, mother, come on, okay? But that's what's going to happen. So as you put resistors in series, the overall resistance goes up, current goes down. In contrast to that, if you put resistors in parallel, the resistance goes down, but the current goes up. Now, let's change this up a little bit. So now, instead of a 10 ohm, I'm going to hop that up to a, let's say, a 20 ohm. Okay? Oh, come on. Work with me here. 20 ohm. So, now, look at this. I got a 10 ohm and a 20 ohm. These are in series. So now when I do the math, I'm going to take a 10 ohm and add that to a 20 ohm, and I'm going to get a 30 ohm. So now that's equivalent of having one 30 ohm resistor. So now when I do this, I'm going to take those 10 volts, still a 10 volt battery, and I divide that by 30 ohms. Oddly enough, that's 1/3, which is 0.33 amps. Okay? That's what we have here. So notice that that current is down to 0.33. Now, notice also with this current, if I put that current there, in between those two, it's still 0.33. I put that current up there, it's still 0.33. So no matter where I measure that current, that's still going to be 0.33 as long as nothing is branching off. Everything is simple. Boom, here you go. Now, talk about the voltage drop though. So notice on this voltage drop here, notice that this is 3.33 volts. If I measure the voltage drop across the other one, notice that that's 6.67. Now an interesting thing happens. This was 3.33, that was 6.67. So what's happening now with Fish and the analogy of the Skittles, this is 10 ohms. Fish is going to lose fewer Skittles crossing the 10 ohms, and he's going to have a bigger Skittle drop across the higher one of 20 ohms. So, but the current's still going to stay the same. The current's still 0.33 no matter where you put it. The current's the same. So if you look at this in terms of furring it up, you have a 20 ohm resistor. You have a current of 0.33. So if I take 20 times 0.3, oddly enough, you're going to get that voltage across there of 6.67. Same thing's going to happen here. So the overall, here's the big picture. The overall voltage drop across both of them is still 10. Okay? So if you hearken back, if you have parallel resistors, they're both going to have the same voltage drop as the battery. You have a 10 volt battery, 10 volt, 10 volt, boom, there you go. If they're in series though, the overall voltage across everything is going to be the 10 volts. But each one individually is going to have a separate voltage drop that's proportional to the resistance. The more resistance that it has, the more voltage it's going to drop. But it's still going to be the same. Now, here's the difference. If they're in series and I cut that, everything stops. If they're in parallel and I disconnect one of them, it stays on. Now, I'm going to stop this for a second because I've got to redraw this whole thing for a problem that you're going to have on your assignment. Okay, this is the setup of question number 6 out of today's assignment. And yes, Louis, it's on page 754 if you want to look at it, okay? Because I know you like your page numbers. So if you want to look at this situation, it's on page 754. So I built the simulation, and here's what I've got. I've got a 9-volt battery, and I've used light bulbs. They're both have an internal resistance of 10 ohms, and there's the electrons flow out, there's a branch. Right now this switch is open, okay? So this part is dead, okay? Nothing's happening here. So let's do the math. So if you look at this, basically these two bulbs are in series, okay? 10 ohm, 10 ohm. So this is like having a 10 ohm resistor and a 10 ohm resistor. Add these together, that's an equivalence of 20 ohms. So I've got a 9-volt battery. So if you VER it up, okay, if you VER it up, then that's like having, because they're two 10s, that's like having 20. So if you take those that 9-volt battery, and you divide that by 20 ohms, okay, you get 0.45 amps, okay? And that matches with what the program has. So here's 0.45. Now, if you want to calculate the power that's dissipated in each one, okay? So if you want to do the power thing, and let's do that. So here's our setup. Light bulb, switch, light bulb, boom, battery, 9-volt, 10 ohm, 10 ohm, okay? So if you look at the PIV calculation, so we've got a 0.45 amp, let's screw that whole thing up, PIV, okay, pretend that that's not there, PIV. So I've got a current of 0.45 amps. Now, if you want to look at this in terms of voltage, so if we come back over here and we look at the voltage, so notice that this is dropping 4.5 volts across here. If I measure the voltage drop across the whole thing, okay, that's reading -9. When you do the lab and you get negative voltages and that flips you out, just switch the leads, boom, 9 volts. And again, that's going to match up with what we said. Fish is leaving with 9 volts. He's going to lose half his skittles here. He's going to lose half his skittles here. The total skittle drop is going to be 9. So, if I want to calculate the power in each bulb, there's one option that I can do, is that I can pivot up. I take 0.45 times that voltage of 4.5 volts, and you get 2.03 watts, okay? Now, that's an option. If you remember, if you VER it up, and you solve for, if you take this for voltage, and you go power equals I times IR, so that becomes IR times, or I squared times R. If you do the same thing, if you take that 0.45 amps, and that resistor was, that's going to get squared, and you multiply that by that 10 ohm resistor. Let's see if we can't hopefully not break physics, times 10. Oddly enough, I still get 2.03 watts. Didn't break physics on that one. Went with the OGC, the original gangster calculator. That one did me a solid. This one screwed me over. OG, we were good. Okay. Now, here's the question. That wasn't the whole point of the question. The whole point of this lab is this. I'm going to close this switch, okay? I'm going to close this switch. So what, and I want you, and I wish I was here for this prediction, okay? But I'm going to make a couple of predictions about what I think is going to happen. So I'm going to close the switch. I want you to all to predict what's going to happen, okay? Pop, I know you're going to have an opinion, okay? Heaton, you're going to have an opinion. You're just not going to say anything. Louis, you're going to be going, is there an L involved? I don't know. No, length of the circuit is not a factor, Louis. There's no L involved, okay? So just focus here. Morella, Gracie, I'm counting on you to be the voice of reason in this whole deal, okay? All right. Whoa, we're back. So I'm going to close this. So here are your options. I'm going to close this. Option number 1, this bulb goes completely out, and this bulb just stays the same brightness, okay? I'm going to close this. This bulb goes out. This stays the same, okay? Option number 2, I close this switch, and then absolutely nothing happens. Everything just stays the same. Current's going to flow here. Current's still going to flow there. Because this is in parallel, everything's going to stay the same, and nothing's going to change, okay? So I close the switch, nothing happens. I close the switch, this goes out, this stays the same. Option 3, I close the switch, this goes completely out, and this bulb grows brighter. Option number 4, I close the switch, this one goes out, this one gets brighter, okay? So that's going to be the prediction. So here's the whole key. This switch is going to get closed, okay? So I want you to think this through, all right? I wish I was here to mediate this argument. So I'm going to close this. Question being is, what are the electrons going to do when I close that switch? What's the path they're going to take? And then, how is that going to impact the brightness of this bulb? Now, this is what I love about this particular computer program, is that if the bulbs do glow brighter, it visually shows it glowing brighter. Okay, so, drum roll please. So hopefully you all have argued, said, hey, what's going to happen? Okay, here we go. So, close the switch. Close the switch. Right now, I'm going to close the switch. Here we go. Ooh, look what happened. That bulb glowed a lot brighter. This bulb went completely out, and that bulb glowed brighter. This one went out. Okay, so here, we'll do this again. Tap that. Okay, open up that switch. Same brightness. Boom, boom. Here you go. I close the switch, this one goes out, that one glows bright. Now, if you think this through, it's taking the path of least resistance. So, notice that a couple of things changed. Number 1, let me open that up. When that current was split between, when it was in series, I had a current of 0.45. When I close that, notice that current goes up. It goes back to 0.9. So this is like Brooklyn was home. If you go with your analogy, Jackson, Brooklyn was home. Brooklyn leaves. Jackson's the lone child again. Okay? And Jackson's going to go bright. He's like, woo! I'm back to being the chosen one again. I get all the lasagna. Jackson's happy. Okay? He's going to glow brighter. Okay? Now, mathematically, let's figure this out. So I got a current of 0.9 amps, I got a resistance of 10. So if we pivot up, okay, or let's do this. So now I have a current of 0.9 amps, and that's going to get squared, but it's still a 10 ohm resistor. So I'm going to multiply that by 10. And then if I do that, I take the OGC, and I get 8.1 watts. Look what happened to the wattage. Wattage is an indication of brightness. So when I had two bulbs, each one was 2.03 watts. One bulb by itself, that wattage goes up to 8.1. That bulb is now bright. So keep this in mind when you work problem number 6 out of the book. You're going to close that switch. So there it is with it open. Okay. Current of 0.45, voltage is 4.5. Now an interesting thing happens. Also when I close that switch, notice that that voltage goes up to 9. Okay. Voltage goes up to 9. So now fish is dropping all of that voltage across the one light bulb. Now that goes up to 9 volts. Okay, kids. Enough of this. I still have to record another lecture before I can go home today. So here's going to be the assignment, which is going to be due tomorrow. Wrong one. Where'd it go? Where'd it go? Where'd it go? Hold that thought. Okay. So this is out of chapter 23. And this isn't too bad. Okay, for reference, it took me this and this, okay, so not horribly. So you got questions 1 through 8. Problems. Yeah, you got problems. 1, 2, 3. And then just do 5A. Okay, just do 5A. And then 10 through 13. Now, when you get to question number, or problem number 1, they're going to ask you, they're going to give you some situations and ask you to draw a circuit diagram. And there's a bunch of examples in the book. So like you're going to have some capacitors. So capacitors are different from batteries. So when you draw a capacitor, you put the two lines that are the same length. If it's a battery, you have a short side and then you have a long side. So that's how you can tell the difference between a capacitor and a battery. A resistor is just like a squiggly line like this. If you're going to have a light bulb, depending upon the situation, typically you just draw a circle and then you put a curly Q in it to indicate that it is, that there was like that filament inside of there. Some people like to draw bulbs, okay, and they do that. So on your diagram, you're going to have, like on this first one, you got a 75 ohm resistor, a 50 ohm resistor, and a 100 ohm resistor. Make sure you label what those are. Just don't draw squiggly lines and think, I'm going to know what's going on. Make sure that you label what's the value of the capacitance, what's the value of the resistor. Don't just draw them and go, oh, Burkamp will know what they are. No, Burkamp won't know what they are. Make sure that you label the values of the capacitors, the value of the resistors. Okay. Let me give you a hint. Your answer to number 12 on the problems should be around 15. Okay? All right. We will chit chat tomorrow. I'm going to stop this and start uploading this video.